talk about computing volume using the cylindrical shells method. So before we jump into any examples, I have kind of a summary at the top of the page here. This formula right here, integral of 2 pi RH, this is the backbone of this whole process. So the 2 and the pi are always in your integrand, and then the r and the h, and of course the bounds of the integral, are what you're filling in problem to problem. So the R and the H are the radius and height of one cylindrical shell, which is kind of this like toilet paper tube shape that I've roughly sketched over here. So this is supposed to be a tube that's like like a toilet paper tube where it has like very negligible thickness. So it's almost like a piece of paper that's been folded into this circle. So the radius of that tube is the distance from the center out to the edge, and then the height is going to be the height of that straight edge. Now, we have some extra information here that starts to make things like a little bit more intimidating. So for this method, if you're rotating about either the y-axis or some other vertical line, so you're rotating kind of horizontally, you're going to compute with respect to x. And if you rotate the other way, so about the x-axis or some other horizontal line, you'll compute with respect to y. This is actually exactly the opposite of what we would say if we were using the disk and washer method. So you could kind of memorize the 4 combinations, or to kind of summarize what's happening here. Normally what I do is let the radius determine what variable you're in. So I'm going to say let R determine dx or dy. And by that, I mean, in each problem, your radius is going to be much easier to express either as just x or y, and that's going to set the variable. Okay, so I have my first example here. We can see a sneak peek of the picture under it here. So I'm going to compare this to a very, very similar situation next, where we rotate just about a different line. So for now, what we have is the region between y equals e to the minus x squared. That's this line here. And we only care about this part of it, but I've kind of shown with dotted lines what the rest of that graph would look like. So between that graph, the x-axis, the y-axis, and the line x equals 1, so we have this region here. And we're told to rotate it about the y-axis, which is indicated here with that red dot. Okay, so what this 3D shape would look like if we take this and start rotating it around the y-axis, we'll get kind of a mirror image over here, a rounded front, and then rounded all the way around here. So the bottom of this thing is sort of like a perfect drum shape with vertical sides. And then at the top, it's going to kind of taper off to sort of like a bullet tip at the top. Okay. So if we were doing the other method, so we're going to do shells today, but if we were going to do the disk method, we would think about slicing it this way and coming up with a formula for the area of one of those circular cross sections. What we'll do is cylindrical shells. And I always start, even though it's really awkward to do, I always start by sketching one shell in the shape, because that gives me enough of an orientation to decide the R and the H. Okay, so one thing to remember as we attempt to sketch one representative shell into this image is that the axis of rotation, so in this case, it's the y-axis we rotated about, that's going to be dead center in every single one of the shells as well, right? So this stick is my center, and then we just have really small tubes coming through here. And then the very widest tube would be the drum edge at the very, very widest radius, right? So if we pick, just some point in between, this is what an intermediate tube would look like. So it has vertical sides, because that's what all these tubes will have. The y-axis goes perfectly through its center. And then it's kind of sitting on the x-axis, because all of them are sitting on the x-axis the way that this bottom was shaped. And we can see from this image, an x value would set whatever that far right edge of the tube is. And once that's set, you've just got your mirror image on the other side. Okay, so now I want to think 2 pi r h. So first we'll think about the radius, especially because we said that's going to inform us if we should be x or y, assuming we don't want to memorize what's happening up here. All right, so for this tube, the radius is this distance here from the y-axis out to whatever that point is there. And if we draw it down below, we can see that distance is exactly just the x value that has set that edge there. So my radius is just x. So that tells me, oh, okay, so I should do this problem in terms of x. So from here on out, everything I choose should be in terms of x, which means when I describe the height, it should be an x function. When I set up my integral, it'll be x values dx. All right, so now let's think about the height of this tube. This will be vertical height here from here to here. All right, so in this picture, the height of this tube is certainly the y value of that point. But we said everything has to be in terms of x. So this is where I'm actually going to pull the formula for that function and say, okay, well, in terms of x, that height is e to the minus x squared. That's going to give me whatever this y value is. So altogether now, I have 2 pi r h. Everything's in terms of the same letter x, so I put a dx at the end, and then my last step is to choose the first and last x values to hit all of these tubes. So any value for x you pick here will set one edge of the tube, which defines the whole thing. So I only need to integrate 0 to 1, because, for example, if x equals a half, that covers the mirror image side. Right? So this is going to integrate just 0 to 1, just those positive x values. So for this, the sake of this video and keeping things moving, I'm not going to compute these actual values. I will say, though, if you wanted to start computing this guy's antiderivative, it would be a u substitution where you plug in for that negative x squared to get the ball rolling. Okay, so let's contrast this with a very similar situation. So I'm starting off, this picture got pretty messy, but we're starting off with the exact same region. This little curvy part is once again e to the negative x squared. And then I have the y-axis, the x-axis, and x equals 1. But now we're told to rotate it about x equals negative 1. So I'm going to have kind of this big empty space in the middle. This is going to go off the page, but hopefully you at least get the idea. So we have this completely empty dead space in the middle, and then it's going to kind of swing around. Over here is the rest of the shape. So this sort of still has that drum shape at the very bottom where we have perfectly vertical side, and then the top of it kind of curves up, but instead of having like a perfect bullet tip at the top, we have kind of this just dead zone where you could see straight through it from above. All right, so we're still going to think 2 pi r h, and we're going to draw in one of our tubes. So now this tube right here, this is the smallest radius tube possible. This is the very first one. And then as we extend, another tube kind of intermediate would be here. So it's a little bit lower and a little bit wider. This is not my best artwork, but hopefully it gets the point across. And again, an x value right here will determine that right edge of that tube. So for 2 pi r h, I think, all right, well, what is the radius of the tube that I've drawn? And now it's not just x, right? So the distance x is going to get us just to the y-axis, right? This distance right here is x. And then the actual radius is extending all the way to the center, which is at negative 1. So whatever that distance x is, it's always that plus 1. So here the radius is x plus 1. So I'm still going to do everything in terms of x. I just have a slightly messier radius situation to deal with when we plug it in right here. Okay, the height of this thing should be consistent from the previous setup, right? So, oops, no, yes, the height, there we go. So the height of this tube is still this distance here. So it's still the vertical height. So that height, it is the y value of whatever that x is. But we want everything in terms of x. So I'm going to sub in e to the minus x squared instead of y. So now we'll set up our volume, 2 pi r h. And now bounds of integration are the last step here. I'm still going to integrate 0 to 1, even though we're kind of way over here. All those x values from 0 to 1, which are these here, they're setting the rightmost edge. So x equals 0 is still that innermost hollow edge, and then x equals 1 is your outermost. So it really does still cover the whole shape. All right, let's try one more example where we rotate the other way. And again, we won't memorize whether this should be in terms of x or y. We'll kind of figure it out as we go. So what we have here is a halfway decent sketch of y equals x squared plus 1. That's just this little tiny piece of parabola here. And it's going to be, or the other two sides of our region are the line y equals 1 and the line x equals 2. So it creates this little triangular type shape here. And this red arrow is indicating that this is going to rotate about the x-axis. So if this region rotates about the x-axis, we once again end up with this kind of empty tube in the middle. And then it kind of swings around like this to make like some kind of like megaphone or like horn shape. But it has this empty tube going down the middle. So the innermost tube here, or cylindrical shell rather, is going to be this tube here. That's your smallest radius. And then the biggest one, like when they go out and out and out, will be right here, really, really narrow. All right, so if I'm going to draw one representative cylindrical shell kind of halfway through, remember the axis of rotation goes through the center of all these shells. This tube shape is actually helping my eyes see which direction they're going to go. They need to be fully contained within the shape. So if I pick one, maybe like here-ish, be like that. So this blue kind of toilet paper roll looking thing, it has no thickness, right? So don't get distracted by the rest of the image. We're seeing radius this way, height this way, and it has 0 thickness. So it's just the blue. It should go down to the edge. Okay, it's not great, but again, it's enough. We're going to think 2 pi r h, and we'll think about the radius first. So the radius of this tube is now going to go the opposite direction of what was happening before. Right, so the radius of this tube is this distance all the way, or sorry, this height all the way down to the x-axis. That's your radius. And that is, so this vertical distance, this is the y value of whatever that point is. Now, if we back solved this for x equals a function of y, like we could switch this if we wanted to, but certainly this works a lot nicer by just saying it's the y value of whatever point you're at right there. So I'm going to do this whole problem in terms of y. And again, if you don't like making that decision because you find this setup really difficult to keep track of, the other option is to kind of memorize, right? And say, okay, well, if I'm rotating this way, I must be computing dy, and that'll give you kind of an extra boost in that decision. All right, so now let's consider the height. We want to say this in terms of y. So the height of this tube is actually kind of its like horizontal length this way, right? This is the height of this tube, the way that we've defined height. So this is a horizontal distance, so it's naturally going to be in terms of x, and we'll have to kind of force it. But it's going to be the distance between this flat edge at x equals 2 all the way to whatever that point is that I was using for the radius as well. So if it's from here to here, this is 2, and then this is the x value. So the difference between them is 2 minus x. Here. All right, so it's whatever, all right, so this far right edge is always 2, and it'll be 2 minus whatever this x value is. That'll be this intermediate distance here. All right, this is true. However, we decided we were doing things in terms of y. So I'm going to take this x and swap it out, right? So I'm going to come back to this formula and back solve it for x so that I can swap out x. We would have y minus 1 equals x squared. So square root y minus 1 is x. And that's what I'm going to put right here. 2 minus root y minus 1. Because x and that root are equal to each other, and that's in the variable that I want. Okay, so altogether, our volume is 2 pi r h. This is all in terms of y, so I say dy. And then my bounds of integration are all of the y values needed for all of these cylindrical shells. Picking y values actually makes sense, right? Because up here, we were saying an x kind of sets that vertical edge of one shell. And then down here, a y value is actually setting the no longer vertical, but like the straight edge of this shell. So what y values would we need to hit this whole shape? The lowest is 1, right? We don't need anything inside here because that's empty. And then we'll go all the way up to 5, which is that very last point of this function at x equals 2. I'm going to integrate 1 to 5, and that's my final answer.